will appear at the stage twice. So it is Aaron Fordy who will first give brief introduction on the correlation functions, and then he will have a break, and then he will tell about electrodynamics.
So usually go through these presentations, we usually jump from making couplings to RRR files, but there's usually one more step in between, and that's making correlation functions.
There is slide advancer.
Oh, right here.
Okay. Escape.
Oh, okay, so just very brief technical details. So I didn't know what a correlation function was until like a year ago, so I assume like a lot of undergraduates might not know. So basically it's just a measure of how similar a quantity is in space and time over different time periods. So like if you have one function at time t and you have another function at t plus like a dt, and it just measures like how similar they are at different times. And they don't have to be different. These can be like f and f, and that would be an autocorrelation function. That's usually what we do. And so the big deal is we use autocorrelation functions because rates of electronic transitions you can use those to, or you can use correlation functions to determine rates. So this guy's a rate, and then this guy here is a fancy way for autocorrelation. Essentially, like if you go through a textbook and read it, all this contains like information from Fermi's golden rule. So it's just another way to write Fermi's golden rule. So that's why we have.
What's the difference between correlation and autocorrelation?
Autocorrelation is how it measures its similarity with itself in time or space, and a correlation function necessarily doesn't have to be with itself. It can be with another function.
So if we change it to G here, it will be autocorrelation?
Yes.
And would you agree or disagree that there should be some exponential with time?
I won't disagree. Okay. So yeah. So and then this is just a nice way to visualize what an autocorrelation function does. So this first plot is just a plot of an autocorrelation of a wave pulse. So how do I?
Oh,
it's still on the marker.
To draw?
Yeah, it's still on the marker.
Okay.
There we go. So this is the plot of an autocorrelation function, and then let it go a little bit. So these are two wave pulses. So at t0 they're on top of each other. So you start out initially at 1, and as you go through time, the wave pulses go out of phase. So you get negative correlations because you're multiplying a positive and a negative number. So you get a negative number. Go through again. They come back into phase a little bit, so you get a positive number again. They go back out of phase. Then after some time, they don't know each other anymore. Then if you plotted those...
So your autocorrelation is, or correlation is red times blue and integrate over the whole space.
So yeah, you basically just add it up at each time step.
Okay.
And then keep going. Then yeah. So if you plotted the values of the integrals at each point, it would do something like this. So this is in phase, out of phase, somewhat back in phase, and then this, they have no idea they're next to each other anymore.
Nice.
And so to make autocorrelation functions from the wave cars that we use, so the MATLAB code is pretty standard. It hasn't changed at all since I've been here. Correlation V3H, and you have to give it coupling, or all the coupling files that you generated. And then you just need energy pop, and you may need overlap, you may not, I can't remember, but I just usually put it in there anyway, because you need it eventually. So you feed it in these files, and it outputs some correlation functions of orbitals with each other, and basically takes all those correlation functions and converts it into an RRR. And to run the code, it's pretty robust. Basically all you have to input is some specifics about about the orbitals that you're using. So you enter your HOMO, max and min from your input overlap, and sometimes you just have to change like these loops just to load in the coupling files, depending on how many you have. So if you have 1,000, there's another loop below this that goes up to 1,000. And if you have less than 1,000, you just have to tell it which number or else it'll yell at you. And so if you run the script and it runs pretty healthy, this is a pretty typical figure. So it starts out at 1, decays very quickly, and then kind of oscillates. And then each of these colors are one of those core underscore homo files. So these are just correlations of autocorrelations of orbitals. Ones near the gap anyway, which are usually the important ones we look at. And that should be it.
So can you go back to this last slide? Let's thank Aaron just in case. And, if we remember presentations, well, some of us made presentations, remember presentations by Levi on dephasing, especially Javid should remember it. Their autocorrelation functions were decaying much slower. So what's were the dephasing autocorrelation functions presented by Levi and autocorrelation functions presented by Aaron applied to the same type of functions or to different characteristics?
So I've always assumed that dephasing was between different pairs of orbitals. So yes. I don't know, for Redfield tensors anyway, they have I, J, K, L. So dephasing would be like the time that I and J are dissimilar from
so
K and L.
Which function, autocorrelation of which function are you showing here?
So you say the black one is like homo and homo minus 1.
Autocorrelation of non-adiabatic coupling.
Yes.
Your couplings file.
Yes.
Okay, and Levi and several other people, dephasing were applied to energy of orbital. So not the coupling, not the transition, but just energy of orbital, how it slowly changes in time. Mm-hmm. And autocorrelation between orbitals, and correlation between couplings behave on very different time scales. Okay. For orbitals, it lives for like 10, 20, maybe 50 femtoseconds. For couplings, so the main feature in this figure is that everything drops rapidly within 1 or 2 femtoseconds. So there is no correlation. The couplings, as Aaron defined, do not know about each other after a couple of femtoseconds. So the system has no memory.
So I'm just wondering why isn't it better to look on the fast Fourier frequency rather than looking on the autocorrelation functions?
Well,
it will be white noise.
Then, but you can see the frequency, how is the overlapping, the same frequency or different frequency. But in this case, what is the quantitative result from these autocorrelation functions?
Well, mostly this quantity here is what we're interested in.
I mean, how can you interpret this, what's the word, vibration, or this quantitatively?
So you can see initially at some time it decays really quickly, and then over time they kind of come back into phase with each other. But if you run this long enough or you get good enough statistics, over time they should average out to 0. So like this is just like, view it as statistical noise.
The reason for these oscillations is accumulation of electronic phase, and electronic phase accumulates really quickly on like attoseconds. So if one would redo this figure on the fraction of femtosecond, like doing it from 0 to 1 femtosecond with step of 1,000 steps, one would see continuous function with slow decay and maybe analyze it somehow. But this ultra short time ranges are not yet in our focus for practical applications. If one would model the free electron X-ray laser for sub-femtosecond processes, one would do modeling on the really short time steps.
But if we take FFT of this autocorrelation function, FFT, I mean fast Fourier transform of these autocorrelation functions, which one would be more convenient to read this information? This one or of FFT?
Or which information?
I mean, for us looking on how many different frequencies involved on these things.
Unless you can visualize Fourier transforms in your head. Like you probably couldn't do it from this, but I mean you can.
In order to do Fourier transform, you need to shorten the time step 100 to 1,000 times. At this resolution, it is almost like a noise.
Okay.
So the only importance is the absolute value of couplings when they are laboring in time.
Any other questions?
More questions to Aaron? If no, let's thank him once again. And according to the schedule, we have presenter number 4, Dr. Fatima. So she will tell the practical steps, how to, she will focus on more details on how to convert this set of coupling files into the matrix of rates which will be used to propagate electronic state. Is there a slide advancer with laser? Okay, good.
So I'm going to talk about how to convert non-additive coupling files to ordered field tensor. This is the theoretical method. So the on-the-fly non-adiabatic couplings are computed using this equation. Here we can see 2 K points, 2 different set of K points, but the rest of the equations I used only 1 K point because for red field tensor calculations I used the code for momentum constant system. So here in this case K equals uppercase K equals lowercase K. And the second equation, this one is autocorrelation function, and the Fourier transform of this autocorrelation function is the transition rate, and these transition rates are the components for calculating red field tensor. So in order to calculate red field tensor, we need all the coupling files, a couple of 100 files. So, and energy pop file, and the energy pop file should contains energies of states, which energies of states that are we interested to calculate. Oh, energies of states, those are used to calculate for coupling files. Actually import a file. Suppose if I have 700 states, 150 states, and if I am interested to suppose 30 states lower the HOMO and 30 states above the HOMO, 30 states below the HOMO and 30 states above the LOMO. So those states, this energy pop file should contain the energies of those interested states. And another file we need, that correlation MATLAB code. Here is the code. So we need to modify a couple of values here. The HOMO, the state number of HOMO, and a maximum minimum state, maximum state, and number of coupling files. Here we can see 3 for loops, This one for just 1 digit, this one for 2 digits, and this one for 3 digits. Since I had 700 something files. And then you need to put all these files to MATLAB directory in your local computer, and then run the correlation code. Then you should get this RR file and this PDF file. And you can modify this code for plotting the rate tensor.
Okay, that's thanks, Fatima. Daniel has a question.
I'm sorry, I still don't understand what I see whenever I see those types of diagrams. What is it telling us exactly?
Here we can see the states, 10 states below HOMO and 10 states above or LOMO. We can see the probability of population transfer. Okay, so suppose for I indices we have suppose 60 orbitals, and for J 60 orbitals. So here we can see how the electron can transfer. We can see that electron can transfer to the adjacent state since the off diagonals are 0. Suppose for this bar, this is HOMO -4, I guess, and this is also HOMO -4. So they are the population transfer to the adjacent states.
So probably it's HOMO -5 to HOMO -4.
Yeah, they are ±1.
Yeah.
Not like from electron cannot transfer from like HOMO -5 to suppose HOMO -10.
Well, it can, but the rate of such
No.
is very low by several orders of magnitude.
Yeah, and this bar is the probability. How
So the
high
bigger
the
the bars,
probability is.
the faster it goes.
The probability is
Okay.
high.
More questions to Fatima? If not, let's thank her once again. And after a little break, we have the same person on stage. Thank you for volunteering twice. So right now, London and Daniel may establish practical questions. Suppose we do have this RRR file with rates of transitions, but we do need occupations of orbitals as function of time, and maybe average energy of electronic system to see how the energy dissipates in lattice vibrations, how charge transfer happens, like what to do with this RRR file, with this set of rates.
Yeah, so this is just getting results from our dynamics, so it doesn't go in depth how it exactly computes the rates for all these, but it's just showing where the relevant parameters are that you need to change to generate the figures to analyze later. So the needed files that you need is, so there are a lot of dynamic script names floating around, but this is usually the most reliable starting point to start with, is this one. And then usually if there are changes, there's additions after the 3. So depending on what you use.
So what does it mean HSP at the end?
I don't know, I've always thought about it, but nothing quick came to mind, so.
Maybe you wouldn't remember.
Yeah, because previously she was a group member at USD. So I guess she modified this code.
So it's abbreviation of the name Huang Shuping.
Yeah.
Oh, okay. I had seen that name.
Okay.
And then this must have been his 3rd attempt.
Probably.
So if you modify the script, just add your initials after.
If you discover an error, it'll be your name, named after you. So this is the general script to use for dynamics, and then you just have to feed in a couple of files. So input overlap, energy pop like normal. So then the last two talks talked about how to make RRR, so we feed that into the dynamic script. And then for visualization, sometimes you want the band out. That would be for like standard VAST calculations, and then there's also been an update that Dimitri has been working on for spin orbit coupling band outs. And that's not in this script, that's a different one. So if you do need that at some time, you can contact one of us, we can take it out from somewhere.
Can you briefly, in like one sentence, summarize what is standard band out, and how does it relate to main interest of London, charge transfer?
So band out basically just takes power charges, which are written as 3D in space, and it just compresses them into 2D, and usually,
Or maybe 1D.
or yes, it's 1D. So it projects them along X and Y, and then we can see along Z. So usually, whenever we make models, if we want to look at stuff like landedness for charge transfer, you have your hole and acceptor and donator along Z. So
And band out is just one file that summarizes all orbitals together.
Yes. So it reads in all the par charges corresponding to your energy pop or input overlap.
Mhm.
And band out, there's a Perl script somewhere in the bin. And then for these, there's a MATLAB code that you have to use to generate this.
So one of the band integrate scripts generate this band out.
Mm.
And if you want to inspect the transfer of charged carriers, you will need to create this file. You just skip it right now to be short and fit in time.
Yeah, so then you feed in these files, and then the outputs that you get if it runs healthy is energy relaxation, and for your average energy of your carriers, and then where they go in space as they relax, which is from the band outs, and then it also computes rates of relaxation from your initial conditions to the band edges. So when you first load up the script, this is what it looks like to begin with. So you have I, H, and IE. So those are just your initial conditions that you choose for your hole and your electron. And I forgot to mention in this, but 1 in both these cases is HOMO and LUMO. So if you wanted to do HOMO minus 20 to LUMO plus 20, it would be 20, 21, and 21. So whatever your LUMO plus Y is, you just add 1 to that for IH and IE. So, and then, well, in principle, you could just do a bunch of random numbers and put them in there, but just to save time, good numbers to do would be orbitals from your oscillator string, so most intense transitions or transitions that you're interested in looking in. So that depends on your system, and it's just something you have to know as you're processing the data. And then some parameters that you have to change depending on the system, so Z steps and Z size. So Z size is from your postcard, so the size of the Z dimension. And then Z steps corresponds to your band out, so it's the number of like grid points along the Z axis, so your resolution basically. And you get that from band out, so whatever the size of that is. And just a couple other things you have to input to your HOMO, and then Omin and Omax from your energy pop file. And then a couple other parameters you can play with. So there's time steps, so that's basically your resolution and time, so how many like increments it does. So I don't know, I've never had to mess with it too much, but depending on how fine a data you want, you can increase this by just increases the runtime of your simulation. And you might get small variations in your rates just because, well, if you don't run as many steps, you're in coarse grain, so you might miss some transitions. So the higher that you increase time steps, probably the more accurate your results are going to be. So you can play with that until your rates are pretty consistent, and then optimize it that way. And then, so that's the number of grid points in time, and then you can also change the length of your dynamics in time. So generally, stuff we're interested in occurs on the nanosecond time scale, and that's what this is set up for at the moment. But if you wanted to increase, like say you wanted to go to millisecond for some crazy relaxation, So he would just increase this until, well, I put a halt in a strategic place and just keep increasing the number until it goes to where I want. But you can figure out other convenient ways to change this number too. So changing this box number increases the time of the simulation. And then those are really the only other two parameters worth messing with in the program. And then if it runs healthy, so this will pop out at the bottom. KE and KH are your rates of the electron relaxes to the band edge, which in this case should be NA. Like these don't correspond with each other. And then K hole would be the time it goes from here to here. So if you do have like 2 multi-relaxation steps, like it won't give you one for each. You have to do some extra legwork to be able to get those transitions. So you get rates, you get these pretty figures. So this is relaxation in energy space. And then this would be for a band out from like a standard calculation. So blue is your hole. So you can see at the time the hole goes out, the electron stays down. So that indicates you have a charge transfer that occurs in your simulation. So that should be it.
Okay, let's thank her. Any questions? Can you go to the last slide? If I would see it for the first time, I would be able to follow interpretation of the first green figure, where your y-axis is probably energy.
Yeah, so when you run these, there are labels on them, but I usually cut them off when I post-process them. So yeah, I would say this is energy, this is log time.
Okay, and for the second green figure, what is y-axis?
So this would be like your z size.
So it's Cartesian, it's z coordinate.
Yeah. So this looks like, I don't know, 15, so 30.
In angstrom?
Yes.
Okay.
So basically the z component of your postcard is what it should be. And then the x-axis is again log time.
And green means that electron and hole are approximately in the same space region, or they compensate each other. But if it splits onto blue and orange, it means there is some charge transfer.
Yes, that's what it indicate anyway. Usually you want to take like a VMD of your model, you just kind of place it so it looks roughly the same, so you know for sure that it's charge transfer.
Okay. More, okay, David?
So how did you calculate the relaxation rates?
So, well, that was one of the prefaces for this presentation. I wasn't going to talk about how the code does it, but basically it just, so it takes all the input orbitals and it produces like a superposition based on your initial condition, and then it does a time step, takes the RR file, computes relaxation from, like, if you're at LUMO plus 20, and they would calculate the rates of relaxation to all the orbitals below it,
Oh, no, up to
or
frontier
possibly
orbital.
above it.
I mean, up to LUMO, frontier orbital.
Right, and then it just does that each time step. So it's a average relaxation rate. So at each time step, it doesn't compute a new rate. So it's the same rate throughout this whole simulation.
So you calculate relaxation every time step, and then
Yeah, so you give an initial population, or do you want to say something?
Oh, no, complete your explanation and then I'll intervene.
So the way I understand is you tell your initial population. So you do a time step, tells the RRR tells it where to send the population, does that again. So then you have like maybe 3 bands that are populated a little bit, and then RRR tells population from those where to go. And then you just kind of get a steady, well, usually you get like a steady waterfall of population of your bands.
but that population is not maybe initial population is maybe 1, final one maybe 1, but intermediate is that 1, or is like
It's,
fraction of
Fraction because it is
It
distributed
is
between several
distributed
orbitals.
so the sum should be 1.
yeah.
So if we repeat same activity next year, maybe waterfall picture would be helpful to understand what is going on.
Yeah, I thought to put it in, but I guess I just didn't. So
Just to keep addressing question of Jabet, what are the dashes and solid line, and how are they related to the rates of transfer or relaxation?
So those are energy expectation values for each. So dash just for electron, and then solid is energy expectation value for holes.
Mm-hmm.
And so based on those, you can calculate relaxation rates.
In that case, rate is changing with the time, right?
Yep, but you can feed it to different functions, starting from the simplest mono exponential, but you can also try to select more complicated fitting function.
And we assume single exponential, well, for regular, like from this code.
But in this case, seems like your whole relaxation rate is not a single exponential.
Right, but basically what it calculates, it takes the time from here to here, it just takes the inverse of it. So you have this relaxation from here to here, but you don't have any information about the intermediate.
Then how about the electron relaxation rate? Because it seems like it stayed on the same energy over time.
Yeah, it doesn't. So the initial population was LUMO, that's what the initial condition was. So then it's already at LUMO,
So
so there's no relaxation.
energy relaxation rate for electron is not reasonable in this example.
Right, because it's
Because it's 1.63, seems like it's a, yeah.
Or maybe you started from LUMO plus 1, something like very close in energy.
I think this figure I was trying to do a waterfall for this image, so I didn't care about the electron. So this should be like if you're doing like a real calculation, like from an optical transition, like this would be up here. Relax now. This is not something we would publish.
More questions to Aaron? Daniel? London? Okay, let's thank Aaron once again. And we have 2 talks for the next 15 minutes. Number 6 is by Dr. Han, is about how to convert the outcome of electron dynamics into some observables related to experiment. So Aaron already told how to assess the rate of energy dissipation and how to visualize the dynamics of charge transfer. But there are also important process of photoluminescence related to relaxation energy. And right now we will hear quickly how can it be assessed.
Yeah, so to calculate the photoluminescence spectrum, we need 5 input files. So the RR energy bulb and also bandoffs are the same as the one mentioned by Aaron. So I guess the special code is this code. And also we need this for master EQ. So this is just oscillator stress in matrix format. So here, how can we get the for master EQ? So basically we find this information from geometry optimized model, and then we can just run this code, and then we end up with for master EQ. This is how it looks like.
Excuse me. What is the dimension of this matrix? I mean, which dimension is what is?
I guess this is just
Number of orbitals times number of orbitals. It's square matrix. But if you use not all orbitals but a window, active window, then it will be number of orbitals in active window squared. Look, if you see symbols, the diagonal is 0 because there are no optical transitions from orbital to itself.
So this is just standard procedure. So we need to transfer these files to a local PC and just run the code. So I guess the code is basically the same as the one mentioned by Aaron. I guess there is some small fraction added. So I guess you do not need to modify it. The only input you need to modify is just the initial conditions. So if the code is running successfully, then you can get this kind of figure. So this is the time resolved emission. So at each time step, we can see the emission. And this is time integrated emission. So it is taking the average of integration. And the final figure you can get is time resolved exciton picture. So, for example, if you have initial condition from LUMO minus x to LUMO plus x, from LUMO plus x to HOMO minus x, so as time goes by, finally you will have transition from LUMO to HOMO.
So the probability of excitation for excitation at given energy to exist at given time.
Right. So it's just an electron hole pair.
So 0 would be like the energy of your HOMO orbital.
No, this is the energy difference.
Oh, between the occupied.
Yes.
Okay.
Okay, this is my final one.
Okay, thank you. Any questions?
So I guess the color changes. What does that mean? 'Cause, like, I guess it starts off red, then it goes yellow, green, blue, 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 to back to yellow to red. What does that mean necessarily?
So blue means there is no emission, and red means the emission is very intense.
Okay.
So it relates to our discussion with Jabet. Blue means 0, red means 1, and if it is in between, it will be rainbow colors. But if at the given time there is more than one electron hole pairs occupied, their probability is less than 1, and it is smeared between them. So their absolute value is less than 1, and therefore colors are like greenish or something exotic.
So, one thing, what is the lifetime of this thing? I mean, these calculations, it seems like it's too long, isn't it? It has started relaxing after 100 picosecond. And then went to the HOMO like 10,000 picosecond.
So
I mean, is it real calculation or for example only?
This is the real case. I guess this is has long, very long lifetime because this is for the less than ions.
Mm.
This is for less than ions in sodium neutral fluoride.
Okay.
how does it correspond to experimental lifetimes? Is it shorter or longer or?
I cannot remember, but I guess we underestimate the lifetime.
So subgaps, it is very specific experimental system, dielectric with single ion, and there are very big subgaps, which take a long time to overcome. More questions to Yun?
I have a question. So if we call this oscillation dipole a script, then we should get oscillator strength, right? And this Formaster equation also.
Yep. So what's your question?
Like if we call this script oscillation dipole script, so we should get oscillation strength as well. Like if I suppose if I want to calculate this spectrum,
Answer is yes.
then I can see there is a Formaster equation also.
Huh?
We can see there is a Formaster equation, Formaster equation file also. We can
Yes.
use that one for photoluminescence calculation.
Yes. So oscillator strengths and this Formaster equation contain the same information, but it is stored in different formats. If you allow, I will answer. So when you are looking onto oscillator strengths file, it writes data in
For the dynamics group,
form
that's
of
what it is. So it's, yeah, that's why it's saying that.
And then we
like number, HOMO, LUMO, oscillator strengths,
So the equations, yeah.
energy like 3 electron
Called like
volts.
master equations.
And then it continues data with only one oscillator strength in each line. But if you're looking in this for master optics, it is a square matrix, and the transition between HOMO and LUMO will be just one element where all orbitals are indexed on the rows and columns. So main diagonal exists of zeros, and one of this sub-diagonal element would correspond to HOMO to LUMO transitions. So it's denser form of to store information.
Okay, I have another question.
Please.
So for my, I believe Yulon doesn't know it.
Huh?
So I have a question for you. So for my model, I have 4 different K points. So I need to calculate that spectrum, UV spectrum for 4 different K points. So how to calculate photoluminescence? Then we need to modify the code.
If you believe, if you assume that there is no indirect optical transitions, which could be right, then you still need the 4 master equation files for indirect transitions, but you can fill them with zeros. But still, it should be same format as your 5 times R. Like R for non-radiative, and I don't know how you would call it, 4 master equation.
4Q.
Yes, yes.
It's not about this one, but I mean, it's a question after listening your answer. So what is the means of optical indirect transition? Is it possible to indirect transition, optical transitions?
No, only if you design photons that have change of momentum.
Yeah, that's understood. So that means there are no optical indirect transition, obviously, in a real system.
I haven't seen that. Maybe they exist.
No, I'm just asking. So
It's good approximation to assume that there are no such transitions.
it is also true for real
On
systems.
very short time, there could be virtual processes with that violate some conservation laws, but in overall,
Yeah, no.
more questions to you? If not, thank you once again. And last but not least, presentation number 7.